Hello all, welcome to the Microwave and Radar Engineering subject lecture 4. After the completion of this lecture, you will be able to distinguish the resistance and reactance circles in a Smith chart, plot the impedance and admittance on a Smith chart, and use the Smith chart to determine the values of VSWR, reflection coefficient, maxima, minima position, and impedance in a transmission line. The Smith chart was developed in the year 1939 by the scientist P.W. Smith as a graphical tool to analyze and design transmission line circuits and the parameters like VSWR and reflection coefficient, etc. Today it is used to characterize the performance of microwave circuits, but in this course we will use it to obtain the impedance matching parameters for single stub and double stub cases in the transmission line. Many professional versions of the Smith charts are available on the internet. This is one of the copies of that. Now let's start with the Smith chart parametric equations, that how this Smith chart is first developed by the scientist P.W. Smith. We know that normalized reflection coefficient tau is equal to ZL by Z0 minus 1 upon ZL by Z0 plus 1. The reflection coefficient value is equal to ZL minus Z0 upon ZL plus Z0, but I am taking here the case of the normalized. It means I will divide my impedances with the value Z0. So I obtain the value as ZL bar minus 1 upon ZL bar plus 1. And similarly, if I obtain the normalized value of my load impedance ZL in terms of my reflection coefficient, it will be 1 by ZL, 1 by tau L upon 1 minus tau L. Now why I am using here the normalized? Because this Smith chart works on the normalized values. If we have to plot the impedance, if we have to plot the admittance, that value is nothing but the normalized value. It means every value over there or on that Smith chart is divided by the Z0. Now, so rewriting these equations of ZL and tau in real and imaginary terms, if I write ZL bar as R plus J of XL or simply RL plus J of XL as it is related with the load, so I can rewrite it as R plus J of XL on the left hand side, and on the right hand side I can rewrite this reflection coefficient tau L again in terms of real and the imaginary term. So real term will be added with the 1, that is 1 plus tau of R plus J of tau of I, and similarly in the denominator. Now rationalizing this term, I will obtain the values of RL and XL. RL will be 1 minus tau R square minus tau I square divided by 1 minus tau R whole square plus tau I square, and similarly XL will be equal to twice of tau I upon 1 minus tau R whole square plus tau I whole square. Now by further solving, this involves a lot of steps, so I am not writing all these steps over here. This is for you. You can solve these two equations, and when we solve it we can obtain these equations, which are nothing but the equations of circle. The first equation that I will obtain from the RL, this equation is tau R minus RL upon 1 plus RL, where RL is the real part of your ZL bar or the normalized load impedance, plus tau I square equal to 1 upon 1 plus RL whole square. And by solving this XL part, we will obtain this equation. So if we compare it with the standard equation of the circle, that is x minus x naught whole square plus y minus y naught whole square equal to a square, we can conclude from here that this is x naught, the value of y naught is 0 over here, and the value of a is this one. Similarly over here I will conclude that x naught is 1 and y naught is equal to 1 by xl, whereas a equal to 1 by xl. It means now we are having two types of circles over here. One circle is obtained through this equation, and other kind of circles will be obtained through these equations. So now we are going to see that what these circles are. This is first is the constant resistance circles. As we can see in this equation, one equation will correspond to the real part. You can see here this real part is RL, and in this the part is imaginary, that is x of L. So by solving this real RL part or RL equation, we will obtain the constant resistance circles. These constant resistance circles will have their center at x naught and y naught, where x naught is this one and y naught is 0, and the radius is 1 by 1 plus RL. So we will obtain these kind of circles. You can see for the different values of R, I have plotted it. The maximum value of R can go on the right hand side up to infinity at this point, and the minimum value is R equal to 0. Similarly, for the second equation, that is this one, for the imaginary part of XL, by substituting different values of XL, I will get different types of circles which are like this. You can see here that if this is my borderline, you can see here that if this is the borderline, then all the circles above this are having the value in positive, that is x equal to 4, x equal to 3, x equal to 2, and x equal to 1. And as I am increasing the value of the x, the circle radius is also increasing. Whereas if I am moving below this line or this border line, then I am moving in the negative direction, and as I am moving towards the higher values of x in the negative side, then the radius of the circles are decreasing. It means these are giving me the reactance circles, where these are all the inductive circles and these are all the capacitive circles. Now if I combine these two resistance and the reactance circles, I will get the value, or I will get the figure like this, in which I am denoting here two kinds of circles, one with red color and other with the blue color. The red color circles are all my resistance circles and blue color one are my reactance circles. So the resistance circles are obtained using the equation tau of r minus rl upon 1 plus rl whole square plus tau of I whole square equal to 1 upon 1 plus rl whole square. This equation represents the family of constant resistance circles with the center at rl upon 1 plus rl, comma 0, and the radius is at 1 upon 1 plus rl. Similarly, these blue color circles are obtained from the other equation, which also denotes a family of the circles, but in this case, these are the resistance circles with the center at 1, comma 1 by XL and radius is 1 by XL. So I forgot to write here XL. So this is the actual radius and the centers of these circles. Now, this is the combined Smith chart, or a professional version of the Smith chart, in which we can see that we have these resistance circles. You can read over here the scale of the resistance circle. For example, this value is zero point 0.1 over here. It means the value of RL over here is zero point 0.1. This value is RL equal to 1. And if I move on to the right hand side of this, I will obtain the higher values of RL. This is 2, this is 3, and so on. Similarly, for the imaginary circles also, you can find the values over here. This is value 1, this is decreasing 0.9, this is 0.8, and over here it is increasing. So if I look at the imaginary circles or the reactance circles, these are like this. This one is for the value 2, this is for the value 1, then next is for the value 3. These are the positive, for the positive values of the XL, and when I move to the negative values of XL, I will get the values as this. This is for -3, this is for -2, this is for -1. And similarly, if I talk about the resistance circles, then let me change the color of the pen. Then you will find this circle. This is at 0.6, so this circle will move over here and it will pass through this point like this. So this will give us the value of the resistance circle. And if I move towards a higher value of the resistance or the value of RL, then my radius will be start decreasing. And if I move to the lower value, my radius will increase. And this value is for RL equal to 0, whereas this value is for RL equal to infinity. It means that I can obtain the maxima and minima over here. As I said over here, the value of RL is equal to 0. It means this point is for my Z minima. Whereas if I talk for this point where my RL is equal to infinity, it means this point is my maxima, Z maxima. Now, this is what I have already explained you, that these circles or these lines denoted by these arrows are nothing but the positive XL circles, and these are the RL circles. RL circles are always positive, and the lower half of this or below this bottom line, we will obtain the negative XL circles. Now, as I said that over here the resistance is 0, so I will obtain here the minima, Z minima, or in terms of voltage it is voltage minima. Similarly, over here, the resistance is maximum. So get Z maxima and the V maxima. Whereas if I talk about the case of admittance, if it is maxima, then in the case of Y, it will be minima. And similarly, in the case of minima, the admittance case will be maxima because they are inverse to each other. Now look at this diagram. Now, first thing that I am going to do here is to plot the value of ZL. Now, as I said, these values of ZL are nothing but the normalized values of ZL. In the Smith chart, we can only plot the normalized values. So, for example, if the value of normalized load impedance is equal to 2 minus J1, then I will obtain the value of 2 minus J1 in this Smith chart by dividing this value as 2 is nothing but my real value, and this 1 is nothing but my imaginary value denoted earlier with the x value, and this is minus over here. It means this x will be negative and it will lie in the lower half of this Smith chart. So let's first find the resistance circle with the value 2 or r equal to 2. So we will see on this axis this is 1. So when I move to the right hand side, I will find that my value will start increasing, or the value of r will start increasing, and this is 2.0. It means on this circle, or the circle denoted by these dotted lines, will contain the values where my resistance will lie the same, or the value of r remains the same, that is equal to 2. But I want my impedance or this x part to be equal to minus 1. So I will try to look at the minus 1 circle. So in this part I will going to hear that this is my minus 1. It means on this circle also my point should lie. So definitely here I can see that 2 circles are intersecting at this point. So this point will be my point corresponding to 2 minus j of 1. So this is how we can plot the value of an impedance, or to be more precise, normalized impedance on this Smith chart. I have done this for to make you more clear by using an example where ZL is zero point 0.1 plus J0. So you can see here again that this is zero point 0.5 axis, and this time it is positive. So it is lying on the upper half of the Smith chart. And this, if you look at this circle is zero point 0.1. So this point I will obtain here is zero point 0.1 plus J of 0.5. Now next is to obtain the VSWR circle. Now this VSWR circle is obtained by simply taking the center at 1.0 and making a circle with radius equal to my load, or whatever the impedance is given to us. I will extend my arc or my compass up to this point, and then I will make a circle. So that circle is nothing but my VSWR circle. Why I am taking here the load only? Because the value of load is available to us. If in the question I have been given a different impedance, for example Z in impedance or impedance at any point, there is no issue. You just plot that impedance on this Smith chart, draw a circle again from the center 1.0 and the radius of that circle up to that impedance, and then draw the circle. This circle will remain the same. It means for all over the length of this transmission line, or for all the points on this transmission line, my VSWR value should remain the same. So that's why I can plot this VSWR circle through any value of my impedance. Now by obtaining this, after obtaining this VSWR circle, we can see that this VSWR circle is cutting this line at 2 points, one over here and other over here. So if I look at this right side point, then the value at this point will give me the value of VSWR. So we can obtain the value of VSWR by simply looking into the scale over here. That is my circle cutting on the right side of this, and the value can be read as the value of VSWR. In some of the Smith charts, you will find that a scale is there in the bottom of the Smith chart like this one. This scale can also be used to read the value of the VSWR. For example, in this example, as I have obtained the value of ZL equal to 0.1 plus J 0.5 earlier, now by extending my compass at from the center 1.0 to this, I will draw this circle, and I will see here that this point is also giving me the value of the VSWR. If I read over here in this line, over here I can see that this point is almost equal to, I think, 12. And if I extend this point, or on the left hand side where it is cutting the VSWR circle, if I extend it to the below scale, then also I can find here that there is a VSWR scale, and I can get the value of VSWR over here, or somewhere over here, that will around, I think, 12. Yes, this is what I have done over here. So you can read this value and it is equal to 12. Also, if you read it from here or at this point on this scale, but now this time we don't have to extend it downward because it will have a different value. You have to just read it on this scale, on these values you have to read. So it will also be equal to 12. Now, next is to find the value of the reflection coefficient. Again, if you look at this, there is one more scale of reflection coefficient, but this scale is giving us the magnitude of the reflection coefficient, that is only the value of rho, and we know that reflection coefficient is equal to rho e raised to power j of theta. So we can find the value of rho over here. It is 0.84 in this example, and to find the value of the theta, we will simply extend our line from the center 1.0 to some point, or for example, if I want to find the reflection coefficient value at load, so I will extend this ZL point, so that will cut the outer circles, and some scales are given over here, and one of them scale is in the theta. So this theta value is equal to 126 over here. But you will find here that when we move in this VSWR circle, the value of theta will change, and that is quite obvious because reflection coefficient is having different values on the different points on the transmission line. So exactly at the load, we can find the reflection coefficient value, that is tau of L, it is at the load, is equal to rho e raised to power j of theta. Rho is equal to 0.84 over here, and e raised to power j theta is 126 degree. Now next is to find the voltage maxima and minima from the load. In this example, the ZL value or the normalized value of the ZL is 2 plus J1. You can easily find this point over here, that is A point. And I have already told you that this point is for maximum resistance, that is infinity. It means Z maxima will lie over here, and over here the resistance is 0, so Z minima will lie. So obviously when the maximum impedance is there, then that point will correspond to voltage maxima, and the point where minimum impedance is there, that will correspond to minimum voltage. So as I'm at this point A and I can move on this circle, that's this VSWR circle, which is nothing but similar to moving on this transmission line. So first I want to find the value of maxima. So there is one convention that when we are at the load and we are moving towards the source, then in the Smith chart we move in the clockwise direction. Whereas if we are moving from source towards the load, then we move in the anti-clockwise direction. So over here I have the value of the normalized load impedance. It means I'm going to move from load towards the source, and I have to find the value of maxima and minima. So I have to move in the clockwise direction. So when I move in the clockwise direction in this Smith chart, the first point where I will obtain the value of maximum impedance or the maximum voltage is this one. Or you can say that I have to do a rotation of some value defined over here in terms of lambda. If we extend this line and we cut the lambda scale, then we will find here that the value of lambda is 0.213. And then by moving this line towards in the clockwise direction, when I reach here, then I have done a rotation of 0.037 of lambda. It means my first maxima, or this value of Dmax, is equal to 0.037. Similarly, if I still move in the clockwise direction, then I will reach to this point, and this point is nothing but my minima. So from here to here, I will move to this point, or to be more precise, I'm moving from this point to this point. That is my first minima. Then the number of lambda that I have moved, that is from 0.213 to 0.5, I will take a difference, and that will come out to be equal to 0.287 lambda. So this minima will exist at 0.287. There may be number of minimas and maxima in a transmission line, because if I do further rotation over here, and I will reach back to this point, and then when I will further move, I will again reach to this point. This is my second maxima, and further moving again over here, I will reach to second minima. So what I have to do, I have to add the value of the lambda. The number of times I do the rotation, I have to add lambda by 2, because one complete rotation in a Smith chart is equal to lambda by 2. It means I can read the scale for one rotation through the outermost scale present over here in terms of lambda, and if I'm doing more than one rotations, then I will simply add lambda by 2 into that value, and I will get the maximas and minimas. Now next is to find the impedance at some length of the transmission line. As I told you that if the transmission line is this, and I have some impedance or the load impedance over here, this is ZL, and if I have to move in towards the source, then I will move in the clockwise direction. I have obtained this value of ZL in the previous example. I have obtained it as 0.1 plus 0.5. I have also obtained this VSWR circle. Now I have been told to move a point, or over here it has been told to determine the value of ZA. It means exactly at the value equal to 0.1 of lambda, I will move, or I will reach to the value of ZA. It means now I have ZL over here, which I have plotted here, and I have to move towards the source. It means I will move in the clockwise direction, but that length or that movement is defined over here as 0.1 of lambda. So I will read the value of the lambda over here, that is 0.075, and I will add 0.1 in it. And when I will add 0.1 in it, I will reach to a point equal to 0.175. So it means while moving in the clockwise direction of 0.1 lambda, I will reach to this value of lambda. And when I will connect this point to this 0.175 lambda scale, then I will cut the VSWR circle over here, and the value of the impedance over there will give me the value of the input impedance. You can see here the point where I'm cutting this VSWR circle can be read from the scales of this resistance and the reactance circles, and this is equal to 0.4 plus J 1.9. It means I can obtain any value on the transmission line if the length is given to me, or any value of the impedance on the transmission line if the value of lambda or if the value of the length is given to me. So this is how I can obtain any value of my impedance Zin, ZL, or at any point using the Smith chart. Now similarly over here I have to obtain the first maxima and the first minima as I've at this point ZL. Then to find the maxima I have to move in the clockwise direction. But if I've been told to find the value of maxima from Zin, then I will move from here and I will reach to this point for first maxima, and I will read the difference of these two lambda values, that will come out to be 0.075. Similarly, to find the first minima I will move from here and I will reach here the value of this lambda, and this value will be subtracted and it will come out to be 0.325 lambda. So this is how we can obtain maxima and minima also. Next is to find the admittance corresponding to a particular impedance. Numerically, we can find the value of admittance by simply making 1 by z, but in the Smith chart, we can do this by making a rotation of lambda by 4. Or if we can see here that this is the point of my load impedance ZL, and this blue color circle is my VSWR circle, then exactly opposite point on this circle, or the diametric point on this circle for an impedance value, is nothing but my admittance value. It means by making the point on this ZL and making this VSWR circle and obtaining the diametric opposite point of that point A, I will obtain the value over there at YL. It is easy to you to read now the value of YL. If I look here, the value B or the point B is cutting the circles. For example, if I look the admittance circle, it is cutting at 0.6 over here, this is 0.6, and if I see at the resistance circle, it is somewhere in between 0.3 and 0.2, so I will read it as 0.25. So my YL over here will come out to be equal to 0.25, that is the real part, and it is below that second, or below this line, so it will be negative. So it is minus J of what is XL. This is, I told you, this 0.6, so it is minus J of 0.6. So this is how you can obtain any value of admittance if we have the impedance value. Or simply you can add lambda by 4 also. So we will read the value of lambda over here for the ZL, and we will add lambda by 4. So then also we will automatically reach to this point. So at the end of this lecture, we are now able to distinguish the resistance and reactance circles in the Smith chart. We are also able to plot the impedance and admittance from the Smith chart, and we can also obtain the values of VSWR, reflection coefficient, maxima, minima positions, and impedance in a transmission line.